I'm Dr. Frank Summers of the Space Telescope Science Institute, and welcome to the Space Telescope Public Lecture Series. Our topic, Oumuamua, a mysterious interstellar interloper, presented by Amaya Moro-Martin of the Space Telescope Science Institute. I would like to remind you that the Space Telescope Public Lecture Series will be online only for the remainder of the year 2020. And I would also like to extend a special thanks to our wonderful tech team who makes all of this online experience possible, Thomas Marufu and Grant Justice. Next month, we will have on August 4th a talk entitled Armchair Astrophysics, Finding Physics Far and Wide, where physics exists in the world that you experience, but you may not really recognize it. That'll be presented by Quinn Hart. In September, we'll tell you about a brand new project that's being done on Hubble, a huge project utilizing the ultraviolet capabilities of Hubble called Ulysses. That'll be presented by Will Fisher. And in October, we're going to tell you about the Nancy Grace Roman Space Telescope. This is the telescope that used to be known as WFIRST, the Wide Field Infrared Space Telescope, but it was christened the Nancy Grace Roman Space Telescope. Now, the speaker there is to be announced because we are having a conference on the Roman Space Telescope in October, and the organizers of that conference are going to select one of the special visiting speakers to be the presenter for that public lecture series. If you want to find out the information, well, you can go to our website, www.stsci.edu/public-lectures, and you will find this page here. Important things to know about this page is, like over on the left side, you can find the webcasts, which are both on our YouTube playlist as well as on our STSCI webcasting site. And on the right, you can see the email. This is where you can sign up for the monthly emails that tell you, hey, here's what's upcoming. Basically, it's two emails a month. You can, of course, also find links to our upcoming lectures with all of the title and the speaker and the abstract when we have it. For each of those talks, there is a lot of detail in terms of the description, as well as links after it's done to the STSCI webcast and the YouTube webcast. As I said, if you want to sign up for the email, if you want the email announcements, you can sign up at our website. You can also subscribe to our YouTube channel, and if you are a subscriber to our YouTube channel, you will get notices of our and reminders of our live events. And finally, if you have comments or questions, you can send them to publiclecture@stsci.edu. Our social media channels are available for not just the Hubble Space Telescope, but also the James Webb Space Telescope and for the Space Telescope Science Institute itself. We're on Facebook, we're on Twitter, we're on YouTube, we're on Instagram. I myself do a little bit on Facebook and Twitter, and you're welcome to follow me if you would like. Okay, so now the news from the universe for July 2020. Our first story tonight, a gap in our knowledge of black holes. So, what do we really know about black holes? Well, one of the most fundamental things about black holes that we know is that black holes have no hair. This is called the no-hair theorem. It's really just a statement that there are very few quantities you need to know about black holes. And actually, black holes are completely characterized by their mass, their charge, and their spin. So there's only three things to know about a black hole. And generally, we believe black holes are not charged. They have zero net charge. So it's really mass and spin. And there has recently been a revolution in our understanding of the characteristics of black holes because of gravitational wave observatories like this. This is the LIGO project, which has a detector in Hanford, Washington, and a detector in Livingston, Louisiana. And these detectors detect the very minute very, very, very minute deviations in space-time created by gravitational waves. And the LIGO project was the one that first detected black hole merger. They have since been joined by the Virgo project in Europe. This is the detector near Pisa in Italy. It is an international collaboration from France, Italy, the Netherlands, Poland, and Hungary. And as I said, these detectors detect the very minute fluctuations in space-time when a gravitational wave passes through Earth. And this, for example, was the very first detection of a black hole merger. And from that, we can tell various characteristics of the black holes. So they've discovered a lot more since this very first discovery. And here is a plot. It's a little bit complex, but let me just talk you through it. Okay, so up at the top, those blue things, those are black holes that have been detected by gravitational waves. So you can see they've had a lot of detections of black hole mergers. The purple ones are black holes that have been detected by other telescopes. They call them EM black holes as they're detected by electromagnetic waves, not gravitational waves. Then down bottom, corresponding to the EM neutron stars, the neutron stars that have been detected by electromagnetic waves are in yellow, and just a few neutron stars have been detected by gravitational waves. So you can see there's a good amount of data that they are developing. But recently, in 2019, in August 14th, they discovered this highlighted one. The one in the center that's got that highlight is called GW 190814, which means 2019 August 14th event. And it was the combination of a 2.6 solar mass object with a 23 solar mass object. And it was unusual. And well, you might actually want to think, wait, how do we know these masses? Well, the masses come from studying those fluctuations, right? When two black holes merge together, they produce gravitational waves in very specific patterns. And these are the wave modes that the gravitational waves produced from this merger of 1908-14. And you can see that they're quadrupolar, there's octopolar, there's hexadecupolar, and then there's 32 polar. Why they couldn't just say 4 polar, 8 polar, 16 polar, 32 polar would be kind of easy, but you know, yeah, it wouldn't sound as scientific, right? Well, anyway, so you can see the very definite predictions one can make and analyze the signal from a gravitational wave observation. That allows them to talk about the masses here. But the funky thing here is that 2.6 solar mass object, all right, it's larger than any neutron star we've ever observed, but it's smaller than any black hole we've observed. Matter of fact, people say that you can't make a neutron star larger than 2.5 solar masses. And you shouldn't really have a black hole less than about 5 solar masses. So there's a gap, a mass gap between 2.5 and 5 solar masses that there really shouldn't be anything there. And yet, here it is. We found one. So there's the mass gap in our understanding of it, but this indicates that there's sort of a gap in our knowledge because we have something in that mass gap now. So the question is, this merger was between a black hole and was it a neutron star, or the largest ever neutron star? Or was it a black hole, the smallest ever black hole? And we actually don't know yet. We're still studying it. It's a robust calculation that the mass of this object, but they will have to continue to study it and get more observations from these gravitational wave observatories to fill out our knowledge about black holes. The second story I have for you tonight is called Comets with Two Tails. And you might think that's a typo. That's not a typo. There are two tails I'm going to tell you about comets. The first one involves a project called ATLAS, the Asteroid Terrestrial Impact Last Alert System. Nice reasonable acronym. Some of the acronyms astronomers come up with are very tortured. This one's actually reasonable. And basically what ATLAS is looking for, it's looking for objects that are going to kill us, okay? It's looking for potentially hazardous asteroids that might smash into Earth and cause big problems like you see in some of those disaster movies, right? And it has discovered 47 of those potentially hazardous asteroids. But to do so, it has to scan the night sky really continuously over and over and over again. And it can find other things. So it has found 459 near-Earth asteroids. It has found 48 comets. And it has found a whopping 6,170 supernovae. So monitoring the night sky looking for potentially hazardous asteroids has side benefits in that you get observations of all these other objects. Well, last December, it discovered a comet, and this one is called Comet Atlas, but its actual name nomenclature is C2019Y4. And when folks followed up the discovery observations from last December, they found that Comet Atlas was going to get very bright. And here it is in March of 2020, and it was really bright, and predictions were saying it's going to get very, very bright, and it will be naked eye visible by May. Well, that got the attention of astronomers who proposed to look at it with the Hubble Space Telescope. And the Hubble Space Telescope then looked at it in April. Unfortunately, this was about as bright as Comet Atlas ever got, because when Hubble looked at it on April 20th, it had broken apart. Comets are made of ices and dusts, and they're giant dirty snowballs. And this one obviously wasn't held together enough, that strong enough that it could survive another passage by the sun. So here you can see Hubble's image of it, and it had broken up into about 20 pieces. All right, so Comet Atlas is no more. That promise of having a naked eye comet this year was unfulfilled. Except I have a second story for you, and that's a comet that has just become naked eye visible. It's called Comet Neowise. Its technical designation is C2020F3. And matter of fact, today it was the APOD, the astronomy picture of today. This is a picture from Maroun Habib of the comet over Lebanon. And you've got a lot of people taking pictures these days. It's visible like 3 or 4 in the morning, okay? An hour to 2 hours before sunrise. And they're able to get up and get photographs of it. And this is going to be an interesting comet. They don't know how bright it's going to get. I'm told that next week it will become an evening object for a bit, that we may be able to see it in the evening. I haven't studied this. I sort of added this to my talk today when I saw it was in the APOD. But if you want more details, you got to go to somebody who's more into comet observing than me. And I'm sure there's lots of people out there right now with it. And if you just want to look at the pretty pictures, well, you should go to the APOD site because the APOD site has a link to a gallery of some notable images that were submitted to APOD that could have been chosen as the APOD of Comet Neowise. And actually, this one here, right? That's the comet over the lavender fields in France. And I just love, if I were choosing APOD, that would have been my choice for today's APOD. Maybe I'm particular because I took a vacation to Provence about a little less than a year ago, and we love seeing the lavender fields. And the idea of seeing a comet above the lavender fields, that would be wonderful. Unfortunately, I don't think I'll be going to France this year, but we can at least admire the gorgeous pictures, and it will be interesting to see whether Neowise develops into a really bright naked eye comet, or it just stays at this fuzzy level that it's difficult to see in the night sky, but you got to really go out and search for it. So I encourage you, if that's your favorite thing to do, go out and search for these comets. All right, that's our news for tonight. And let's go to our speaker. Our speaker is Amaya Moro-Martin, and she will be talking about the Interstellar Interloper, Oumuamua. She comes to us from, she is here at the Space Telescope Science Institute, an associate astronomer, and she did a PhD at the University of Arizona. Then she did a postdoc at Princeton, which is where I did one of my postdocs. And then she went to Spain to the Center for Astrobiology before coming here. And she's been here for 6 years. She works in the mission office for the James Webb Space Telescope. And I asked her, what does she like to do? And she has a wonderful hobby that she can still do during the coronavirus times, that she loves to garden. And she says she likes to promote the growth of flowers, weeds, some wild rabbits, and a few children as well. So, ladies and gentlemen, Amaya Moro-Martin.
Hi, thank you very much for inviting me to give this talk. So I'm going to be talking to you about Oumuamua, which is a mysterious interstellar interloper that you probably heard about because it was on the news for quite a while. So in late October of 2017, we were surprised by the discovery of an object that was traveling the solar system so fast that not even the giant planets would have been able to give it such a kick. It was crystal clear that this visitor wasn't going to stay because the sun's gravity wouldn't be able to hold it back. Its orbit was not a closed ellipse like the one for typical of solar system objects, but it was open. And this meant that the object did not originate in the solar system. It was coming from the interstellar space. It was the first interstellar object other than little interstellar dust particles that was ever detected in the solar system. And this was very exciting. And I'm going to show you the object now. Ta-chan! Here it is. This is the object one day after its discovery. Yes, it's just a dot. You might think that at first sight that astronomers get easily excited, but hang on in there. This object was named Oumuamua, that in Hawaiian means something like distant messenger, referring to the fact that it was the first interstellar visitor. What was its message? Well, I would think that its message was that the universe is full of surprises. I was particularly surprised about this discovery because 10 years prior, when very few people were paying attention to the topic of interstellar interlopers, I led a study to try to understand why we had not detected any at that point, even though such an object will have been easily identified because of its distinct trajectory, right? An hyperbola rather than an ellipse. We got to the conclusion in this study that the number of interstellar objects per volume of space was so low that the detection of one of these extrasolar comets will require surveys that go very deep and are able to detect very faint objects. And that was a capability that we didn't have at the time. We still don't have it now, but eventually we would have it. This is the Vera Rubin Observatory, which was formerly known as the Large Synoptic Survey Telescope. It will start operations in 2022. You can see how huge it is by looking how small the person is to the lower right. And also there is an 18-wheeler in there. So this thing is huge. So in that study, we argue that the survey capacity of this telescope might be able to detect interstellar interlopers. So our conclusion 10 years before the discovery of Oumuamua was that this type of interstellar interlopers would be detected eventually, but we needed to be patient and wait. So when the first interstellar interloper was detected with Pan-STARRS, which is this little survey telescope shown here to the left, we were very surprised, very. And shortly after its discovery, we realized that we had gotten very lucky because Oumuamua was actually quite small, about 100 meters in size. So this is a blowout of the orbit. Again, the only reason that we were able to detect it with Pan-STARRS is because it happened to pass very close to the Earth, as you can see here. And this was when we actually detected when it was on its way out of the solar system. We never saw it coming in. And it passed within the orbit of the Earth on October 14th. That happens to be my birthday. So try to beat that as a birthday surprise. It passed at a distance of approximately 0.16 AU, which is about 60 times the distance from the Earth to the Moon. So it was very close. And by that Halloween, it was already beyond the orbit of Mars. A colleague of mine refers to Oumuamua as a bat from hell. Well, that is some fast bat. So we were surprised by its discovery, but what we didn't know at the time was that this initial surprise will turn into utter bewilderment. So, because it was coming from the interstellar medium, where it is only a few degrees above absolute zero, one would have thought that Oumuamua would be icy like a solar system comet. The one shown here is our beloved comet Halley. As comets get close to the sun, part of the ice near the surface sublimates, and this gas lost into space drags along some dust particles from the comet's surface. This creates a coma, a gas tail, and a dust tail, like the one shown here for comet Halley. Because we thought Oumuamua would be icy, astronomers searched for Oumuamua's comet, the gas, and dust tails, but nothing was found. If Oumuamua wasn't icy, then it must be rocky like an asteroid. But soon they realized it didn't look like a normal asteroid either. Based on its brightness and its distance and making some assumptions about how efficiently it reflects light, astronomers estimated that Oumuamua was only about 100 meters in size, smaller than most known asteroids. They also observed that its brightness fluctuated every 8 hours very sharply, at times becoming 10 times brighter. In this video, you see these fluctuations. Some brightness variation is expected because small rocky objects are like rotating lumpy potatoes. At times, more of its area will be facing us and then they will look brighter. And then when less area is facing us, they look fainter. But generally, this brightness variation is quite small. But for Oumuamua, it was very drastic, about a factor of 10. This meant that Oumuamua's shape was very unusual. It was either very elongated, like the image you see here to the left, or very flat. So it was, either like a penne pasta or a pancake. But when I saw food, other people saw this. And now it's going to get interesting. So upon close inspection of Oumuamua, it was discovered that the object was being accelerated like a rocket. This non-gravitational acceleration makes a noticeable difference in the trajectory. I'm going to show you the trajectory of Oumuamua here. The red is what you would expect if there were no excess acceleration, and the only acceleration was that created by the sun and the planet's gravity. While the blue is what was actually observed. You see that there is a big difference. So something that is not gravity is accelerating the object. Now, this jet-like force is typical in comets and is caused by the mass loss that happens on the day size of the nucleus, where the ice is sublimating, because that creates a jet reaction force, and this affects the orbit. But as I pointed out before, Oumuamua did not show evidence of having any gas or dust being lost. Detecting the gas is tricky, but detecting the dust should have been easier, and there was none. So we don't have any evidence that the non-gravitational acceleration observed in Oumuamua's trajectory was caused by mass loss. But then what could be causing it? So there was the suggestion that this extra acceleration could be due to the radiation pressure from the sun, a force that is created by the collective kicks of solar photons hitting on the surface of an object. But this radiation pressure is very weak. These are just photons hitting a surface, right? So for it to cause the acceleration that was observed, the object would have to have a lot of area and very little mass. So it could be pushed easily like a sail. It was suggested that Oumuamua was like a membrane structure of a very thin material, less than a millimeter thick. And because it is quite unlikely that such a membrane could be produced naturally, the proposal was that it was a light cell from an extraterrestrial civilization. I thought about this and proposed that another way an object with very little mass can have a lot of surface area, where the solar photons can impart the little kicks, is if the object had a fractal structure like a snowflake. And this could also explain Oumuamua's odd shape. It will make it very unusual because it will imply that Oumuamua had an extraordinarily low density, about 100,000 times lower than water, and lower than graphene aerogel, which is the lowest density synthetically produced material known. To give you an idea how light graphene aerogel is, you can see this picture here of a piece being held by a flower. So we're talking about a very, very, very light material. So I propose a fractal structure because fractals are found in many forms of nature and are thought to arise naturally because their formation processes involve an element of stochasticity, of randomness, like particle collisions in a protoplanetary disk or particles in a solution. And this is what you see here is an interplanetary particle, an interplanetary dust particle collected in the space. It's about 10 microns in size. Its core has a fractal structure and its formation involves random particle collisions. So what I proposed as an alternative to the light cell hypothesis was that indeed Oumuamua was being pushed by radiation pressure, but that it wasn't a membrane, that it was something like this interstellar interplanetary dust particle, but much larger, on a much larger size. But how could such an object form? Because we know how dust particles form, but we don't know how to form such large objects. So now let me step back a bit and let me tell you, in order to explain how such an object could form, let me explain you how stars are born and how planets are born. So stars are born in molecular clouds of gas and dust. In some region of the cloud, the density is higher, and this makes the region contract under the effect of its own gravity, and eventually this forms a ball of gas that is much denser and hotter than the rest of the cloud. And we call this very dense and hot region a protostar. Around this protostar, there is this envelope of gas and dust that is rotating and contracting at the same time. And this makes it flatten into a disk because of conservation of angular momentum. Here you can see in this image, two disks in Orion seen in silhouette and with a protostar in their center. So the dust particles that are in these disks, remember these disks have gas and dust. These dust particles are very small, about 0.1 microns in size, and they collide with each other frequently. In some of these collisions, the dust particles stick to each other and form aggregates, like the interstellar dust particles shown here, that you can see that this composed is really an aggregate of many small particles. These aggregates collide with each other and grow into pebbles that eventually coalesce into larger bodies known as planetesimals that can be of the size of comets and asteroids. And then eventually, under some circumstances, this can lead to the formation of planets. First the solid cores, and then the giant planets, as the most massive cores start attracting the gas in the disk, forming gaseous envelopes, forming their atmosphere, like the two planets that you can see here forming in this disk. So there are numerical simulations that study this collisional growth of dust particles into larger bodies. And these simulations predict that if the dust particles are icy and are very small, the aggregates that will form will have less and less density as they grow, because they are colliding, they are creating these fractal structures. And when they collide, there is some compression that happens, but you actually, when you collide particles, you actually are creating more vacuum because of this fractal structure. So, and this is what is represented here as the size in this graph, as this particle grows in size, its density drops. So these cosmic dust bunnies, that we can call them like that, like the model shown here, could be pushed by radiation pressure because they will have enough area and they will weigh very little. So the idea that I proposed was that Oumuamua could be one of those intermediate early products of the planet formation process that arises naturally from the collisional growth of icy dust grains. And if it were the case that Oumuamua was a cosmic dust bunny forming the outer part of the protoplanetary disk of another star, it will be extraordinarily exciting because very little is known about these intermediate early products of planet formation. And imagine, it's very difficult. We haven't been able to observe this in the distance. Imagine thinking about the possibility that one of these fragments is coming to us. It's just mind-blowing. So there has been other proposals for Oumuamua's nature. For example, it was suggested that such an ultra-porous object with no gas could be a desiccated fragment resulting from the disintegration of an ordinary extrasolar comet under some conditions. And this ties very well with the news that we just got from Frank, where we were looking at this object that we were expecting that it would be very bright and it disintegrated. Well, maybe Oumuamua is one of these fragments of an extrasolar comet that got too close to the sun and disintegrated. Others have suggested that Oumuamua is made of molecular hydrogen ice and that it could be a cosmic hydrogen iceberg that originated in the coldest regions of a molecular cloud, with the sublimation of the molecular hydrogen being responsible for this rocket-like propulsion that we observe. The issue with this proposal is that it cannot account for the lack of dust, as the molecular hydrogen that will sublimate, that we need to sublimate because it will account for the push, would drag along dust particles, and the dust particles should have been observed, but they were not observed. And it also has been argued that molecular hydrogen is so volatile that such a body could not have been formed in a molecular cloud or could have survived interstellar travel. Another proposal for Oumuamua is that Oumuamua is the result of a tidal disruption event. Under this scenario, a comet-like object would have come too close to its parent star, and the tidal forces of the star would have tear it apart into elongated fragments that could be ejected into interstellar space. And Oumuamua would be one of those, fragments that have been tear apart. So as you can see, we just don't know. We have all these possibilities, but we just don't know. And unfortunately, Oumuamua can no longer be observed. So we cannot get more observations to test any of these hypotheses. So do we expect all interstellar interlopers to be this weird and this fascinating? A second interstellar interloper was detected 2 years after the discovery of Oumuamua. It came even faster than Oumuamua, so it was clearly interstellar. And because its velocity was so high, and because it didn't get as close to the sun as Oumuamua, its trajectory was not bent as much. So you can see it here. The trajectory of this second interstellar interloper is in yellow, and Oumuamua's trajectory is in red. So this is a close-up of the orbit. It didn't get as close to the Earth as Oumuamua, but it was easier to see because it had gas and dust emission. So it had a coma, it has a tail. So finally, we had detected the first interstellar comet, because Oumuamua was the first interstellar interloper, but it wasn't a comet. And this was the first interstellar comet. So it was actually detected, and I find this very curious. It was actually detected by an optical engineer called Borisov, using a small telescope that he built himself. So this is not any amateur astronomer. He was an optical engineer, right? So this faint blob, these are the discovery images. This faint blob moving across the image is Borisov. I mean the comet, not the person, right? And this is also Borisov, but seen with Hubble. It is fuzzy because of all the gas and dust being lost due to its ice heating up. And it looks like a normal solar system comet, except that it's moving way too fast to be coming from the solar system. It is estimated that its nucleus is between 2 to 5 times larger than Oumuamua, that is about 200 to 500 meters in size, but it didn't show any evidence of being that elongated. So it's not that we think that this object had such a drastic elongated or flattened shape. Its trajectory did show a non-gravitational acceleration, but this could be accounted for because of all the gas and dust that is being lost from the part of the nucleus that faces the sun. So its trajectory, there were no surprises in the trajectory. So there was nothing to worry about this object, except that it was very rich in carbon monoxide, richer than almost all solar system comets. And because carbon monoxide is so easy to vaporize, this probably means that this extrasolar comet originated from the outermost region of its host planetary system, where it's very cold and the carbon monoxide can stay in ice form. It was probably ejected into the interstellar space because it passed too close to a large planet in that planetary system. So this is indeed a planetesimal coming from the outer region of a protoplanetary disk around other stars. So how are these objects ejected? This is how we think they are ejected into interstellar space. This is the young, I'm going to show you now a model of the young solar system. The red, yellow, and blue, the red, yellow, blue, and purple lines, the purple ellipses, right? All those color ellipses are the orbits of Jupiter, Saturn, Neptune, and Uranus, respectively. The green dots that are moving here very happily are planetesimals that are located beyond the orbit of Neptune. And as you will see in this video, at about 880 million years from the start of the simulation, there is a gravitational instability that rearranges the orbits of the giant planets and ejects most of the planetesimals into interstellar space. You'll see is going to happen right now. So you see most of the planetesimals are gone. And of course, this is just a simulation, but there is indeed evidence that the asteroid and the Kuiper belts in the solar system today contain only a very small fraction of the objects that were there initially. So there is evidence that such gravitational ejections occur and that they resulted in the clearing of most of the planetesimals in the early solar system. Numerical simulations like this one show that these clearing processes are very common under a wide range of planetary architectures. So it's not only for the solar system, but we expect this to be common around many planetary systems. And this ejections event would most likely take place when the planetary systems are very young and the planetary orbits are still rearranging themselves, trying to look for that stability. So many of these objects would have experienced very little alterations since their formation because they are ejected, these planetesimals are ejected early in their planetary system history. And once they are ejected into interstellar space, these interstellar planetesimals would drift for millions and hundreds of millions of years in the deep freeze of the interstellar medium, where they will remain unaltered. So they will be like time capsules from their planetary system's most distant past. Eventually, one of these interstellar planetesimals would cross paths with the solar system, becoming an interstellar interloper, like Oumuamua and Borisov. And this will offer us, this is offering us the opportunity to glimpse the building blocks of planets around other stars. And this is why they are so fascinating. The frequency of these encounters depend on the number of interstellar planetesimals per unit volume of space. If there is the number density of interstellar planetesimals is very high, then these encounters will be very frequent. So we can actually calculate or have a rough estimate of this number, of the number of interstellar planetesimals per unit volume of space, based on the observed numbers of stars per unit volume of stars of space, and making an estimate of how many planetesimals each star would eject. Of course, there are many uncertainties in this calculation, and we have to do a lot of hand waving, which is something that astronomers do very well. But a generous upper limit would imply that within the orbit of Neptune, there would be about 100 to 1,000 interstellar objects at any given time. And this is where we encounter another of Oumuamua's mysteries, if you didn't have enough. Because we know it passed within 0.4 AU of the Earth. We also know that the Pan-STARRS survey had only been in operation for a few years. And from these two facts, we can estimate that there are about 10,000 interstellar objects like Oumuamua within the orbit of Neptune. That number is between 10 and 100 times larger than what we estimated before from the ejection of planetesimals from extrasolar planetary systems. And the key question that we haven't been able to solve yet is, where is all that litter coming from? So if you have small children in the house, you probably know what I'm talking about. So one interesting idea that has been proposed is that since we have so many planetesimals drifting around in interstellar space, the same way that Oumuamua and Borisov cross paths with our solar system, these interstellar planetesimals would also enter the environments where stars and planet formation are taking place, like these giant molecular clouds or these protostellar disks. And these environments will be very dense. And these incoming objects might get trapped instead of just fly by, like what happened to Oumuamua and Borisov in our solar system. It just fly by. The gravity of the sun and the planets wasn't able to hold it. But in environments like a molecular cloud and a protostellar disk that are much more massive and dense, then trapping might take place. And these trapped planetesimals could have sizes that are large enough to rapidly grow into larger bodies via the direct accretion of the some centimeter size dust grains in the disk. And they could act as seeds for planet formation. So it's kind of poetic, right? You have these remnants of young planetary systems being thrown into space, being cleared out, and these same remnants could become seeds of planet formation in other planetary systems that are being born. And I'm talking about seeds of planet formation. How about seeds for life? Could life hitch a ride in an interstellar planetesimal and land on a planet? Well, there are organisms that are remarkably resilient to the hazards of outer space. Meet, for example, the tardigrade. This is one of the most resilient organisms that are known. It seems that it has like an integrated spacesuit, right? So some organisms, if buried below the surface of the object where they are shielded from the damaging cosmic rays and UV radiation that can really do bad things to the DNA, if they are buried under the surface under a meter or so, they might be able to survive in interstellar space for millions of years in a dormant state. But then interstellar objects have very high velocities. So most of them will burn up in the atmosphere as they get to a planet, right? So there is little hope they will actually land and survive. But there are interstellar objects that may be able to land on the surface. And for this, they would be subjected to very high temperatures and pressures created by the impact shock. But actually, there are bacteria that are able to survive under those conditions. So the transfer of life through interstellar space, even though it seems quite unlikely, is an interesting possibility that at this point, with the knowledge that we have today, we cannot rule out. And I would like to end up with this slide. It shows, it's a tapestry showing comet Halley and dates back to 1066, 1066. So this is almost 1,000 years ago. And it summarizes very well where we are at with respect to our understanding of Oumuamua. And it's pure wonder. But remember that the second interstellar object was detected with a homemade telescope. So probably more of these objects have been detected before, but not perceived. And the same happened to Pluto and the Kuiper Belt objects. They were detected decades before they were actually identified. So now that we know interstellar objects exist, they will probably be easier to identify. And this will allow us to characterize the interstellar planetesimal population and shed light on its origin, and maybe solve all those Oumuamua mysteries. And so I would like to finish there.
Thank you, Amaya. That was wonderful. And unfortunately, I can say you answered a lot of questions, but you also brought up almost as many questions as you answered there. One of the things that struck me, so I always get the honor of asking the first question, was that you showed the simulation that where Neptune kicks out all the objects in the Kuiper Belt region. Now, when I did my undergraduate work way back when, it was sort of implied that Jupiter, being the most massive of the giant planets, was responsible for, say, the Oort cloud kicking out. Was that something I misheard, or is it just this outer stuff that's mostly affected by Neptune, right?
No, actually, it's mostly affected by a resonance with Jupiter.
Okay.
So there is a resonance with Jupiter that swaps through the Kuiper Belt, and it is that resonance, this ability created by that resonance, that clears the object. So it's the interplay between Jupiter and Saturn is the resonance that is sweeping. So Neptune doesn't play such a big role. So it's mainly
Ah,
Jupiter and Saturn that are driving the
but
instability.
Neptune has that, you know, but Neptune swapping orbits with Uranus, which we've known about,
As well, right, right.
makes it look like Neptune's the one that's doing the encounters and the kicking. Okay.
Well, the resonance affects, right, the
Yep.
swapping of the resonance affects the orbits of Neptune and Uranus as well. Right,
All
yes,
right.
yes, yes, that's right.
So now we're going to bring in Grant Justice. Folks that have been watching on YouTube have been entering a lot of questions in the chat. I've only had a chance to check it every now and then, but he's got a lot of questions to choose from.
There's a lot today, yes.
Yeah. So
I
Grant,
think,
pull some questions.
Sure. I think I'm going to limit it down to probably 3 based on the length of the expected replies.
Oh.
So one of the questions I got that was repeated in many different forms was, can you talk a little bit more about how Oumuamua got captured by the solar system?
Oh, it did not get captured. So when you see I can show you, let's see, here, I'm going to, can I share the screen again? Can
Sure.
I put okay, let me do that. I'm going to share the screen. Okay, so can you see it? Yes?
Yes, we can see it.
Okay, so here's Oumuamua in the red trajectory, and it's not captured. It's coming in, its orbit is being bended by the gravitational
Amaya,
acceleration.
I'm seeing your presenter view, not your.
Oh, you're seeing the presenter
Yes.
view. Okay, so let's try. Okay, let's see. It worked before.
It worked perfectly before, but you know, these online presentations always have a question or two that we.
To the
Okay,
gentleman in the chat that was asking if we were live. Yes, we are live.
so let me say it with words. So when Oumuamua came into the solar system, the trajectory got bent, but it left the solar system as fast as it came by, right? So by 15 months after it got close to the sun, after we discovered it, it was already by the orbit of Saturn. So it never got captured. These objects did not get captured in the solar system. They are lost forever into the interstellar medium.
As you called it, a bat out of hell. It just came screaming through the solar system and went out. And
exactly.
You called this, you just correct, this is a hyperbolic orbit.
It's a hyperbolic orbit.
It's an open orbit. It's not a closed
orbit. It's an open orbit, right. An ellipse will be, if it is an ellipse, it will be coming back. All comets come back, or at most they are like almost like a parabola, right? But this was clearly a very open ellipse. Well, all ellipse, I mean, a very open hyperbolic orbit, right? All hyperbolic orbits are open, but this was, and Oumuamua, I mean, its trajectory did get bent because it passed really close to the sun, but it wasn't trapped. So this object is not going to come back like a periodic comet, unfortunately.
So less of a capture and more of like a slingshot orbit.
Yes, it's a slingshot, right? Exactly.
Okay. And is there anything observed that has a similar makeup to Oumuamua that's in our solar system or our universe?
Absolutely
or galaxy,
not.
Rather.
No,
okay.
Absolutely not. There is nothing in the solar system that has the properties that we have observed for Oumuamua. I mean, you can look at the colors, and the colors don't look that different from other objects in the solar system, but clearly with the acceleration that we found in the trajectory, there is much more there than the colors. So no, nothing in the solar system has those characteristics.
So if something like that did exist, it would have been in the early solar system and probably got kicked out. Is that where
right? I mean, yes, exactly. So one of the theories, right, that we put forward was that maybe it was like a very primordial planetesimal platform, and it would have been kicked out, right?
Right.
Yes.
But I mean, saying would those same low density primordial planetesimals have possibly formed in our solar system?
They could have formed, but it's not, I mean, we just don't know, right? Because the planetesimals that we observe now are, what is closest to the primordial planetesimals are comets, right? Comets are wonderful because they've been, they were ejected early in the solar system history, so they have not been altered that much, but comets have a density of about 0.1 grams per second. That's 10 times less than water. And we are talking about an object that if radiation pressure is responsible, I mean, if the non-gravitational acceleration observed cannot be accounted, has to be accounted by radiation pressure, then this thing will have to have a very low density, and it's like nothing like in the solar system, right? And even if it's not, even if you think that there is actually mass loss, and the problem is that for some reason we couldn't observe it, which we still don't understand why that would have been the case. But even assuming that, and assuming that it was a normal object, its shape is very drastic. It's very elongated or like a pancake, and nothing in the solar system that we've observed has such a drastic shape. So it was very unique.
I think that's why it brought so much attention from everyone. So another one here. Do ejection velocities match up to observed values? Or did it pick up or lose speed on the way? We alluded earlier to it being kind of a slingshot orbit, but was that actually the case with Oumuamua?
It would, for Borisov, there is mass loss that would have started when it was approaching, right? So the velocity will be affected, right? And for the case of Oumuamua, something was pushing it as well. So by all means, the velocity would change, right?
So the velocities, are they like they're tens of kilometers per second?
They are, right. So for Oumuamua, it was traveling at a velocity with respect to the sun of about 26 kilometers per second. For Borisov, I think it was more in the 40s, something like that. So it was, Borisov was coming much faster.
So really the time to travel between solar systems would be on order of tens of thousands of years when you're traveling at speeds like that. If you were going directly from one solar system to another,
right.
You can travel a few parsecs in 10,000 years.
Right.
At those speeds.
Yeah.
But how fast does it do the Kessel Run, Frank?
And we don't know where this. Yeah, go ahead.
Go ahead.
No, I was going to say that we don't know where, if you try to trace the trajectory back in time, you may argue, maybe you can trace where it came from, right? We actually can't. It's very difficult to do that because there are a lot of gravitational perturbations, and also the stars are, the stars move, right? So we don't know where this object is coming from. Many people have tried to do that, to see if they can pinpoint like the star or stellar association, what the objects might be coming from. And they try to do that by estimating how fast it would have been. I mean, they want to have like a close encounter, but they also want to have like a low velocity close encounter. And by that, maybe, that's a sign that it came from that system, but they haven't been able to pinpoint the system.
I'd imagine traveling as fast as it is, it would be skipping back and forth between gravity wells and poles of different galaxies. And
what a nice dance, right?
Yeah,
an interstellar dance, right? Yes.
Yeah. All right. So that brings me to the end of the ones I wrote down. Let me check the chat to see. Do we have time for one more?
Okay. Yes. I guess I wrote down a question in terms of the radiation pressure.
Okay.
Because you've got a 100-meter size object, and to get like aerogel out to 100 meters feels like it would be extremely fragile, and then slingshot that across interstellar space. Does the low density have a limit to the size that you can build it?
Actually, yeah. There has been a study to see how fragile this object is when it's subject to, because when it's traveling in interstellar space, you have all these tidal forces and this rotation. You can have disruptional, you can have rotational disruption, and you have these tidal forces. And actually, the conclusion that was that an object with a fractal structure of such a low density could survive. Another thing is what we don't know if if it could have survived the ejection from its host planetary system. That we don't know, but apparently such an object could have survived interstellar travel. But you know, there are many open questions, and unfortunately we cannot observe this object up close, right? I mean, it will be great to have like a spacecraft traveling to one of these objects, and people are actually thinking about doing that. The problem is that these things are traveling very fast, and in order to send a spacecraft to one of these objects, you will basically have to have a spacecraft ready somewhere in an orbit, on like parking somewhere. And ESA actually has such a proposal. But the problem is that even if there is an interstellar comet coming and you have this spacecraft ready in L2, in the case of this mission by ESA, you still need to go to the object. And unless the object gets very close to where the spacecraft is parked, you wouldn't get there as fast. But there are other people that are suggesting to use like really novel propulsion methods, like using a laser from Earth to like push the rocket, right? To push the spacecraft. Yeah, and then also there are other people suggesting to use solar cells. So this will be for a small, you know, spacecraft. But so there is a lot of possibilities, right, that people are exploring, because having a close encounter with one of these interstellar objects will be just extraordinary.
It would be
It's
extraordinary,
important to give some context for close encounter as well, because I think oftentimes we forget when we're talking about space, it's very hard to close encounter in space is such a huge amount of distance.
Well, yes, it's just getting a bit closer, right? So you can do observations that are, you know, you can actually observe it and it's more than a dot, right? Which is the case of, I mean, they're beautiful, these close encounters with comets, right? And you see the comets, they are absolutely beautiful, these odd shapes, and then you see the jets, and it's stunning, right? What this spacecraft can observe. And of course, it will be really cool to do a return mission, but that's even more difficult for an extra. I mean, it is already difficult for a solar system body that is moving at a reasonable velocity. For something that is moving like, you know, like a bat out of hell, it will be very difficult to be able to pick up something and bring it back to the lab to analyze it.
Even just to get observations of it. I know the STSCI scheduling team works very hard to get observations just of something fast moving like Oumuamua, because the entire timeline had to change.
Yes, exactly.
Even just pointing the telescope, much less getting a spacecraft there.
Right. But if JWST, it's, you know, if we have these objects, when JWST is online, that's going to be fantastic, right? And we'll probably have, during the lifetime of JWST, we'll probably have interstellar.
Right, so that brings up a final question, is how many of these do we expect to observe per decade? Okay, so JWST's got a 5 to 10 year lifespan. How many of them will come through the solar system?
We expect about a couple per decade. I mean, sorry, a couple per year. So per decade, you know, it's you know, like
a few dozen.
Yeah, a few dozen, right?
Cool.
So, yeah, so it will, I mean, it's not that you can do statistics with a few dozen, right? But it will help us to start characterizing the population, right? It's very difficult to do that with just one object.
That's how we build science, by, you know, I guess
little
building up the statistics little by little by little.
And you know, these things have probably been detected before, because one thing that I still don't understand is that, you know, Pan-STARRS has been looking for these things. It was part of one of the goals, right? And it's not that these people have been looking for these things before, but they have not been identified. So maybe there is, you know, people going to the archives and looking at the archives, they might be able to identify these objects that were detected in the past, but not identified. So I hope people are working on that.
I'm sure they are. All right, Grant, did we have any more questions, or are we done here? Sounds like we're done. All right, thank you so much. That really, it's an exciting field to know that we're actually studying interstellar interlopers to our solar system, and that there is a great chance of studying others. We can't study one multiple times, but by studying many of them, we can sort of build up the statistics and the understanding of these interstellar interlopers. All right, next month on August 4th, just to remind you, Armchair Astrophysics Finding Physics Far and Wide by Quinn Hart of the Space Telescope Science Institute. Please join us then. And until then, keep looking up and enjoy exploring your universe.